Hello, everyone. This is the review session for the Jan round gold contest. This time the gold level questions are hard. That's why the threshold for passing is 650. So much lower than the typical threshold 750. So basically, if you can solve two questions, then you can pass. Because two questions, you would get 67 points. Right, okay. I'm not sure whether you guys have the preparation for gold. So I might be able to just explain two questions. Or depends. I might just explain one question. Because I see some of you right from the bronze level. So very likely it will be hard to follow me in the process. So please let me know if it is too hard to catch, and I'll slow down so that probably you can get just one question correct. Already? Okay. We're going to go through the first one. Actually, the simplest question for the three problems would be the second question. The second question does not need to have any specific structure or algorithm. Just do a graph traversal. You're going to do it, but you have to remember to reverse the order of the applying the updates, not the forward one, but the reverse order. Anyway, I'm going to go through the first one, which is a DP question. Okay, DP stands for dynamic programming. If you have not done DP before, because I see some of you are from the a silver level and maybe a few from the bronze level. Okay, I guess. Anyway, does not hurt just to get to know the concepts. Okay, so let me explain the question. The drought actually is connected to the drought question from bronze. Okay, you have done that one. The integers here, rather than from the multiple sub-test cases here, we have just one array to work with. N is at most 100. So you might wonder, N actually is smaller. H also would, the range for the height of the hunger levels, right, would also be smaller. Typically, this could go up to a billion. This one could go up to 100,000. But this time, N and H are rather smaller than before. And why this would appear in the gold level? Well, the question asked a different answer. So if you have the integers H1, H2, so here, let me change the color to make it black here. So you have H1, H2, H3 here, all the way through Hn here. We don't know the lowercase h, but we do know the upbound h. So if you have, this is uppercase H1 here, and your level may be here. And this could be H2 here and H3 here. Now, we want to ask, this is Hn. This is 0. We want to ask how many different the tuples. This would be n tuple. So this would be H1, comma H2, all the way through Hn. How many of these tuples so that they can be lowered to the same, we said H0, H0, bring all of these n integers all to 0. Sometimes it's impossible. We have seen this, right? So suppose 0 and 1, 0. If this one is H1, that's H2, that's H3. And every time you're going to bring two numbers down by 1. So here you can't. If you bring this down, it will make it negative, and we'll have to make it all non-negative. Here. To the same non-negative levels. So this is impossible. So here it asks, if you have the restriction lowercase h1 should be no more than uppercase h1, h2 should be no more than uppercase h2, and so on. Satisfying that restriction, how many such tuples? This one is called n tuple, or you can say that's a vector. How many such vectors exist so that they can all brought down to the same h0, where h0 is non-negative? And this number could be very big. So we're going to take the module, mod this 1,000,000,007. So for those in the gold class, in the 4th semester, we did not address this one yet. So we have covered units from 1 through 12. We have done the graph traversal. We have done the shortest distance, segment trees, binary trees, right? All these we've done, but we have not done this DP. DP actually is the most commonly used techniques in the gold level. So we would have 3 units to explore this technique. Okay, since we don't have that one yet, so probably it does not, if you were in the contest in January, so probably did not help you to solve the question. But here I'm going to explain one idea, and hopefully I can go through the code, even though you were not exposed to this idea. For many of you, right, I hope I can explain the idea clearly to you. And please let me know if any part it is confusing to you or you have a confusion. Okay, the DP. Okay, even though we're going to have, you know, a lot of effort emphasized on that one later, but here for this question, I try to explain the idea. Okay, DP basically is recursion, but you're going to remember the results for partial problems. That is, you're going to remember the result for a problem where the input size would be smaller, and you want to save it. Where do you save it? You're going to save it into normally a matrix, or in our case, it would be an array. Can be 1-dimensional, can be 2-dimensional, can be 3-dimensional. Okay, so if you have not used uppercase, I mean, you know, the 3-4 dimension arrays, right? Don't worry, this is common for DP. But of course, right, the most common matrices for the DP arrays would be 1 dimensions or 2 dimensions. But for DP, it is also common to see 3 and 4, 5. Sometimes we would even see 6 dimensions. Don't worry, they would be just a matrix. And you know, since for USACO, the space complexity is also restricted, right? We all know this one. For each submission, you can take no more than 256 megabytes in memory usage. If you ask more space than this one, you would get an error saying runtime error. Okay, so you know, right? If you have an array of 1 dimension, 256 megabytes, if you create an array of integers, each entry, each element takes 4 bytes, so you can have at most 64 million integers. Each one takes 4 bytes, right? That's 256 megabytes. But in general, you're not going to have an array of 64 million because you need to space, right, to store some other part, the rest of your program. So that's, you know, just to estimate, right? The upper bound would be this one here. So 64 million, 1 dimension. If you have 2 dimensions, so you take the square of this one, so you have 8,000 here and 8,000 here. That's 64 million, a square matrix. And if you do 3 dimensions, so take the cube, right? So this would be 400 here, 400 here, and 400 here. Okay, not much, right? So the higher dimension, right? 3 dimensions each, the size of each dimension, right, should be at the most 400. So the more dimensions you have, 3, 4 dimensions, right, then the number for each dimension, the size of each dimension should go down. So don't worry about that one. So if you see a matrix for DP storage, if you see, say 3, 4, 5 dimensions, then the numbers normally will not be big. Okay, so for this question, that's exactly here. We have n at most 100. Okay, so we're going to set up a DP matrix. Okay, this DP, I'm going to explain the idea and I'm going to illustrate how this one can be implemented. So I'm going to have 3 dimensions here. So I'm going to do I and J and K. This idea actually is a combination of what the USACO website says and also Amy's solution, Amy Chan's solution. She got a perfect score for this one. So the meaning for this one, this is actually the number of the tuples, the number of the n tuples. Actually, this one is not exactly n, the I tuples. Where we're going to work with H1 all the way through HI here. So that HI ends at J. J is value no more than 1000 here, because we have this restriction. All the H values would be no more than 1000. Of course, the HI should be no more than the uppercase HI, which is a number should maybe less than 1000. Oh, the goal is to find out the number of such tuples, the n tuples, lowercase h1, h2, h3, all the way through hn. Each one, lowercase hj, should be less than or equal to uppercase hj, satisfying the restriction. And also, each of these n tuples can be brought down to the same level h0, where h0 is a non-negative number. Right. When go through a simple example, for example, you have say 1, 1 and 1, 1. Of course, let's do this one, 2, 2, 1, 1 here. So we're going to bring these 2 guys down to make it 1, 1, and this will be the same, right? So this one works. Okay, you can also write if this is the uppercase h1, h2, 3, 4. This one itself works. This one also works. This one also works, right? You can just bring these 2 guys down to 0. They will be all the same, and then they're all non-negative. Okay, so we're going to set up the this storage here. It will be a 3-dimensional matrix. It has 3 indices, I, J, K here. The meaning is you're going to work with the first I integers, h1 through hi here. They would, of course, right, satisfy the restriction. H1 should be less than or equal to uppercase h1. Hi should be lower than or equal to uppercase hi. For each one, the restriction holds. And also, they could be brought down to the same level. Right? They can be brought down to this h0, where h0 is non-negative. Most restriction, the second parameter, hi should end at j. J should be a value no more than uppercase hi, but bigger than 0. While the others, while h1 and hi minus 1 end at k here. Okay, let me pause a little bit. What does it mean here? Okay, for DP, as I put at the very beginning, right? DP is recursion. So I need to use recursion. That means I'm going to use the smaller values to find out the big values. So from the setup here, what I need to do is I want to find out the when I becomes n, right? Because I have to make sure this would be applied to the n tuple. All the n integers would be brought down to the same level h0. So here I would get this dp at n. Okay, and also here the last value ending at j and the others ending at k. So they should be the same if this one is a valid one, right? So this one should be k here, and this one should also be k. That means the last one, a lowercase h n, should end at level k, and also the others h1 through hn minus 1 also would end up at k here, where k could go from k is actually the h0 here, right? H0 should be no more than the smallest of uppercase h1, h2, all the way through hn. So I'm going to do this one here. So k should go from 0 to the minimum of h. Okay, minimum of h would be the smallest value of h1, 2, 3, all the way through hn, uppercase h. Okay, so that's what I want to find out. So this is, you can say, a three-dimensional array. That's the row and that's the column, that's the layer, right? You can say that's the layer here. You can slice this one. Each slice is a rectangle or it's a square. Or you can say that's the cheese slice. You can cut the cheese, right? That's one slice, another slice, and so on. So this would be the slice index. And this these two indices, right? These two would determine the row and the column. Okay, once we understand this one, right? So here, for each slice, we want to get the diagonal. The row and column indices, right, would be the same. But anyway, I want to get the, we start from the bottom, which normally would be easy, the base case for the recursion. And we want to get the top one. So the top one here, we'll get the diagonal. The top slice would get the diagonal when k is 1, k is 2, k 3, right? The top one is also a slice. And you may have more at the bottom. So this is a slice at very top, and this would be the slices below. So I want to get this one here, and I want to get the diagonal entries. And add them together, that's my answer. Of course, right, when you do the addition, may be bigger than the 1,000,000,007, and we're going to mod this MOD, where MOD is 1,000,000,000 plus 7. Okay, that part, we don't worry about it. Now, how do we find out this matrix? If you want to find out the top row, the last row, I mean, the last slice, you need to start from the bottom. And also you need to reuse the values at the bottom, I mean, below, and find out the entries at the slice that is at the top. So that's the idea. If say this at the top, that's Jack. Jack says, okay, I need your information from, say, John. John says, okay. John, I'd say, Jane, I need your information. Jane says, okay. Jill, I need your information. So basically, right, I would say just layer and after layer, or slice after slice, we just pass the information and propagate the value from the bottom to the top. That's how we do the DP, right? Okay, with this, let's explain the DP relationship. So let me remove this part here. Okay, talk about the relationship. So the DP I and J and K here. How do I use this DPI? I've worked with the, this is from from 1 to I here. Now I'm going to consider the position I plus 1. How do I use this part I have processed so far from position 1 through position I to help the position I plus 1? Okay, if I have, so the meaning, right? So here I can, let me put this one here. So dp and I plus 1 and say x and also k here. Bring this. Okay, so that means for dpi plus 1, I'm working with position 1 through I plus 1 here. The last one is at position x, and then all the rest are at k. So how can I derive from this to this one here? Well, actually, this can contribute to this one in this way. When I was at position I here, position I ended at J. So this was, say, J here, and I'm going to put this one, say, to show the difference. That's HI, that's J. So if I can bring this J down to K here, because I can always, these guys are at K, I don't want to mess them up. But if this one is at J, I want to bring down this to K, so that will make it all the rest, right, should be at K. When I'm at the position I plus 1, so from 1 all the way through I should be position level K here. Myself could be at X. Okay, so when I go from this DPI JK, how to get this one here, I'm going to lower down this one from J to K, right? I'm going to lower this at HI. But if I lower this value HI here, I would have to do the same thing. I'm also going to lower this J minus K at HI plus 1. Okay, so I don't want to go, this one is too small. If this one is not too small, minus this, the difference here, this is the difference. If the difference at H, this is HI plus 1 here, HI plus 1 does not have this much difference to go down, then I would be in trouble, because I would not be able to say, when I'm at a position I plus 1, all the rest would be K, but I'm below. That would be impossible for me to bring it down to everything into level K, right? That's impossible. So there is a restriction, right? So here, J minus K actually should be less than HI plus 1 and minus X here. Right, you go from HI minus 1 down to X here. This part should be more or at least the same as this difference here. If this part is not enough to cover this difference, right, then it will go down. So this difference D here should be less than this gap. This gap should provide enough cushion to lower this part, right? If I lower at position I also have to lower the same amount at position I plus 1. So this is actually I plus 1 minus x. So now x should be, if you solve this one to this one here, x should be less than hi plus 1 minus j and plus k here. That's right. Okay, that is if dpij can help on these guys where x should be in this range. Okay, not all of, not just one of this j can help. Actually, if you want to find out all the from position I and different j can help this one, I'm going to rewrite this here. So change the meaning here. So I'm going to rewrite this j. So j should be less than or equal to k. Change this one here. So hi plus 1 minus x and plus k. That's right. So now I'm going to find out, if I want to find out this, say, this top, this layer slice I plus 1, I'm going to see how many of these, say, how many Johns at this level can help Jack. So I'm going to rewrite. So here, right, I say this I can contribute to this x here. If x is in the range, then would benefit from this j. Now I'm going to say fix the x. I'm going to see what kind of j can help. Okay, so now I'm going to rewrite. This is also a typical, put j here and k here. Okay, exchange. This is, I'm going to rewrite x with j here, and this I'm going to rewrite. So this would be I, and I'm going to say use another variable p here and k, right? I'm going to find out all the p's that can contribute to this dpi plus 1 j and k here. So using this technique, right? So p, replace this j with the p less than or equal to hi plus 1 minus the x is j here and plus k. So all those dp at this slice I, when p is less than or equal to this one here, can help this dp at the next slice I plus 1 j and k. Or if you want to rewrite it one more time, so this is dp, this is I here, this is j, that's k. All these guys can help, would be dp I minus 1, and this is p and this is k. Again, what kind of p can help? P should be less than hi minus j and plus k. All right, so now we're going to use the slices below, right? The slices here, John, Jane, Joe, and so on below, to find out the value at this slice I. This is the slice where Jack is. Find all those guys that can contribute to this one here. Basically, this is actually the summation of all the p's. P is no more than this one here can contribute, and p has to be bigger than k. So here p is big than or equal to k. You have to make sure p is big than or equal to k. You cannot have a j that is lower than k. That's impossible to make it, bring it level, because the operations we can apply, right, will only to lower, to bring down the h Hunger levels. So here, that's the sum we're going to do. So for each layer, we're going to do the summation. All right, so notice we have this matrix I, J, K here. I goes from 1 through n, that's n values, right? Here, J and K would be the levels of the H value. So each one at most can go to 10, 3. N can go to 10, 2. So this matrix has already 10, 8 elements. Each one would involve such a summation, which is the P could also, if using the complexity, right, we have used the big O notation. So this is again big O 1000. So we're going to do another 1000. So this one is way too big than the 10.9. Okay, so now we have to, for those of you, right, I noticed some of you are in from the bronze level. So how do you improve the complexity here? Okay, we can improve by reducing the summation. Okay, notice this one, right? DPI only depends on DPI minus 1. That means it's actually not the case. Jack will depend on the layer of John and also Jane and Jill. Actually, it's not. The slice Jack only depends on the slice John here. So every slice only depends on the value from the slice right below this one here. So actually you don't have to go too much down. And since this one is dpij, right? So here ij will remain the same. This one, I minus 1 does not change, k does not change. The only thing that will change would be the p here. So easily we can have a prefix sum to reduce this part. We don't need to do a linear summation on a loop. Actually, we can just reduce this one to big O1 operation using a prefix sum. So if you can reduce that one, this actually you can bring down to n times, this is the, I think I've used the word, the symbol h. So the minimal h here, even though, right, you say each one can go to 10.3, but actually this number should be less than 1000. So this would be the minimum of h squared times n. So this, you can finish the calculation. Still, okay, one more part is storage. That's right, this one is n, that's 10.3, that's 10.3. Even though this one is not this big, 10.8, as we said, right, we can have at most 64 million integers. This one clearly, right, is much bigger than 64 million. So this is 6.4 times 10.7. This one is already 10.8. We cannot afford to have these. But notice, again, that's another trick in Gold. This layer only depends on the layer right below. Do you have to keep all the layers? You don't. So when you have, say here, the 4 layers, right? When you have Jill's value and find out Jane's value, then you can forget about Jill's value. Just use Jane's to find out, to calculate the John's value. When Jane's value is ready, when John's value is ready, you can throw away the Jane's storage. So you don't have to make this n of them. Rather, you can just take 2 slices here. Every time you have the current value, current slice, find out the slice above. When the slice above is ready, drop or discard the previous line. Always go up. So here, you don't have to do n of them, just 2 of them. So here, that's 1,000 times 1,000, that's a million, 2 slices. So you can bring this down from roughly a million, I mean 100 million, right, down to just 2 million. 2 million, that's okay. That's not a big deal. Okay, so from both ends, we have explained how this question can be solved. First, we're going to clarify that the recurrence relationship here for each dpijk would depend on dpi minus 1 p and k. So that's the recurrence. Once this one is ready and figured out how we can store And we also have figured out, right, this one we can store just 2 slices rather than all of them. And actually, we're going to reduce it even further. Why? Because you don't have to take all of them. You don't have to take all of them. The thing is, actually, this k will also reduce. We can do it n times. Okay, so another argument would be like this. We're going to, oh, right here, the dpn and k here. So k is the level, right? Everybody would be the h0 will have set here. So suppose you bring down everyone h1, h2 down to k here. That's the same as you bring h1 minus k, h2 minus k, and hn minus k down to 0. So this solution, dpnkk, would be the same as dp still to n. Well, this be 0 and 0. Right, because we have reduced, you go from h1 to k, the same as h1 minus k down to 0. But you're going to change. Your h was before here, now you're going to say make it to h, each h will decrease by k. So we're going to run how many iterations? Still the k, right? K goes from 0 all the way to minimal h to see whether it's possible. So now, since they have just 0, 0, you can just do this just one level, dp, run n times, and just 1 here. The j run n times, actually minimal h times. You don't have to do both, just one, that's enough. So we're going to reduce the complexity of the spatial complexity. Rather than having millions, now we're going to have just thousands of the storage. That'll be enough. Okay, make sure this transformation makes sense to you. Bring down hi to k, that's the same as hi minus k down to 0. Then we're going to reduce, rather than having 3 indices, make it just 2. And this one, we're going to run it n times. So the storage every time will be different. So actually, we're going to have just 1 dimension. 1 dimension, that's much, the demand for the spatial complexity would be much smaller. Okay, so I'm going to go through one version of the implementation, and bear with me if this one does not make much sense or it's still not clear. Just walk through, okay? And you might have the chance to go back to the code and then figure it out yourself eventually. So here, I'm going to use a version for C++. Notice right here, I still have the very simple IDE for C++, the Dave CPP, development CPP. Sometimes I also use Guinea. The reason for me to do this one is I don't want to use 2 IDEs. So Eclipse, if you want to do a project where you have to, you want to work on a problem, you have to create a project. And I want to put all the test cases in this project. So normally a question is a project. Okay, this is required for Eclipse. And also if I do say a more powerful IDE like Visual C++, Visual Studio, then also requires you're going to create a project. But I do want to share the test cases. You don't want to, as you have more and more problems, you don't want to have the storage going exponentially. So I'm going to save this, the 2. So now mainly I'm going to use the C++ and the Java version to create projects. But for coding, this one, I'll just use a program. So here the coding and also the debugging for CPP would be much simpler than this one here. Anyway, a more powerful IDE would help you to do the debugging. But for me, probably does not matter. So I'm going to use either way. Sometimes I do coding in this one, Notepad C++, Notepad++, that can also run. And of course, I'm going to do the command window. So many of you have seen, right? I have the batch mode. I can run the program, and then for each input, I'm going to generate the output and then just have another command to check whether they're the same. Okay, so let me go through here. This code actually is not long, with 52 lines. You'll be surprised, right? This question, I've explained such long time, and you can implement with such a simple way. Okay, so the mod, that's the MOD 1,000,007,000, and this is normally the case. This is a number, the smallest prime number that is bigger than 1 billion. So if you do the mod normally, we're going to take this one. The next number, the next prime, right, bigger than this one is 1,000,007,000. Of course, that's a twin pair for primes. N, that's number of the integers. H, that's the height. N is at most 100, so I'm going to create this one at most 101. DP, so we're going to say DPJ. So here, J is at most 1,000. The same thing for the prefix sum. So PS also at most 1,001. Normally, this is the safe way. For USACO, you don't have to actually. You can just make it 1,000, but for most practical purposes, right, we're going to just add 1 or 2. Okay, the input will start from here. That's to make sure we don't do the synchronization, so that will make the reading input faster. Okay, read N and find out, read all the H numbers. Actually, these would be the uppercase H values. And we're going to also find out the minimum value. Since we're going to find out the minimum, we're going to start from 1,000 here. Each number is guaranteed to be no more than 1,000, so this works. Now we're going to do this one for do it once, solve for the each H going down to the lowercase k, right, would be 0. And that's the case when N is even, that will count everything. Okay, here, let me just mention one thing, and then it's easy to figure out. So suppose N is even, you can reach this, say, K here. Then it's guaranteed you can make it down to any number that is below K, right? Say K prime is less than K. If you can, say, bring H1, H2, all the way Hn down to K here. If this N is even, just pair them up. Right, these two guys, you can say both of them going from K, drop from K to K prime. These two guys bring down. So if you can go to K, you can reach all the levels below. And that's enough. If you do another one, they have been counted again. They have been counted already, so don't overcount. So when N is even, just bring it down to 0, that's enough. But when N is odd, that's not the case. For example, right, I can do the example 353. You can bring down to 1, but you cannot bring down to 2. Look at this one, right? If I want to bring all of them down to the same level, bring down by 1 here, that's 4, that's 3. Bring down this by, oh, actually, 2 is enough. Okay, so, no, I'm sorry, 2 cannot. This would be 3, this would be 2. Now, if you bring, that's once, twice, do it one more time, 1, 2, and 2, and you're going to do one more time, so 1 and 1 and 1. So 4 rounds, you can bring all of them down to the same level, right? But it's clear, right? You cannot bring all of them down to 2 or 3. So here for odd N, you do have to try each one here. Every time you're going to decrease each HI value down by 1, and try to find out how many such tuples that can bring everything down to the same level. Okay, so now everything is reduced to this solve function. Solve, giving me the h here. Find out how many of them can be brought down to k or down to 0. Right, we have just said if you want to bring h I to k, that's the same as the new h down to 0. Okay, since we are modifying the h, so actually every time we're going to try to bring down to 0, whether it's possible. Okay, so now go back to this critical part. This helper function only has from 911 to 930, so 20 lines of code. Actually 22 lines of code. Okay, so for each one, we're going to find out the base case when you have just one position. If this PSJ, how many ways you can reach this J, and using what we have said before. So this DPJ is the same as what we have the DPI and J and K here. This J is same as this J. PS is basically the partial sum of this one. So PSJ is basically this DPX, where X goes from 0 to J. And we're going to avoid using the position. Oh, okay, we do use 0 here. So if you want to just bring one position down to 0, depending where you are, if you start from H0 here, right, you can go there. But you cannot go from bigger than H1. For all those that are big than H1, you only have H1 plus 1 choices, right? Basically, you're going to go from 0, 1, 2, all the way through H1 here. So that's the value. For these guys, you can only go from 0 all the way through J, as long as J is no more than H1 here. Okay, that is just for position 1. Basically, right, we're saying process this, the cows H1 all the way through I here. Right, this is what we say. We're going to process the integers from position 1 through position I here. Okay, now for position I that is bigger than or equal to 2, when I is 2. Okay, first we're going to create the DP, the second DP array. Okay, that's for the Jack version. That's the John's version, the slice. So for Jack's, that's the second, the top layer, right? Initially, we're going to fill all of them to be 0. Now we're going to add it together. So this is what we said, right? So the initial one, the P, we said, right? As long as P is less than the HI minus J plus K, when K, we're going to make all of them 0. So this will go from 0 all the way to this one here. So that's the old DP, the slice, the John slice. Now we're doing this one for Jack's slice here. Each one is this here. And this is the partial sum. Partial sum, you go from 0 all the way to this one here. That's the partial sum from the beginning to this. Okay, so now we're going to assign this new DP. So we're going to, when we do this one here, we have abandoned the old value, but we're going to reuse it. We don't actually abandon, but we're going to reuse it. We're going to assign every value to DP2, and then now we still call it DP. Would it be take this partial sum here? Now, for the next iteration, we're going to update the partial sum again. So PS0 is DP0, right? That's typical one. Now for each value that is, actually this one should start from 1, sorry. Okay, for each index J run all the way up, right, should be the same as the PSJ minus 1 plus DPJ here. So this clear, right? That's the prefix sum again. And every time you do so, you're going to mod MOD. At the end, when the loop is done, you're going to return the P as 0, as we said. This will bring down everything down to 0. Okay, so looks like it's not too bad if you can get this clear, the recurrence relationship. But to be honest, maybe not easy to figure out this DP array, especially you want to implement in the 3-dimensional, the I, J, K, where the I is the position we are processing so far, J is the ending value, K would be the value of all the others ended at. So it's not so easy to come up with such a design. There are several other ways to set up the DP array. Actually, a few other students also send me the code. Some of them are working, some of them are not working yet. But I do see some of the ideas. Actually, the ideas are worth the effort to try, even though during the contest, they did not have time to pursue further enough. But I'm pretty sure if they have enough time, they should be able to figure it out. So this one is a rather hard DP question. For some of you that have been working with, say, the technique of DP, then you might get it. But for many of you, right, if you have not done this before, even though you were in the 4th semester of the Gold class, probably still this does not ring a bell alarm in your mind, but that's okay. We're going to spend a lot of time in the spring semester to study this technique. As I said, right, for most techniques, my treatment would be, say, 1 unit for each one, but the DP we have spent allocated 3 units. So that is indeed important. I think I've told you guys before, every 3 questions in the past 6 seasons, you're going to see 1 question that involves DP. So it is worth the effort. Actually, we're going to do unit the 3rd and then through the 5th unit, we're going to do DP. So that will be enough to catch the Feb round and also the March round. Actually, the idea we're going to cover from unit 13 to unit 18, that would be enough to, yeah, we have 7 weeks before the March round. So should be able to finish all the topics right before the US Open round. Okay, so let me clear this one here. Now it is also a good time to take a break. So let's come back in 5 minutes. All right, let's come back. Let's do the second question. The second question, actually, there was a question similar to this one, that is the closing the farm. Which question? Closing the farm should be 2016, 2017. Here, March 2016, that's the US Open round in season 2016. Very similar to this one. Okay, let's see how this question goes here. We have n nodes here, numbered 1 through n, and initially there's no edge between the nodes, and each farm is active. Now we're going to perform the queries. Q would be the number of the queries. Each query can have 3 possible formats. If you have D, we're going to deactivate a node X here. Initially, every farm, every node was active. Now, if you do D, the node X will become deactivated or inactive. You can also add an edge between node X and node Y, but here, notice, if you add a road, you can only add a road between 2 active farms, active nodes, X and Y. You don't add a road in generic way. You're going to see why this makes a huge difference. And then you have the third type of the query, would it be remove an edge to make life a little bit harder. You're going to remember the index of the edge that was added. So you're going to remove the e's letter row edge. So e equals 1, that means the first row or the first edge added in. So you have to keep track of this add the row at the edge. So that's not, the hard part. You can always reinterpret. So remove e, this would be the same as remove the edge between x and y. That's not a big deal. Okay, here the definition for a node to be relative means itself is active, it will be relative, or it is connected to a node that is active, then this node is also relevant. So basically you're going to find out the connected components. All the nodes in the same connected components would share the same status, relevant or irrelevant. As long as one node in the component is active, then every one is relevant. Okay, now we're going to answer the question. For each node x here, find out until which update, which query it stays as relevant. So very likely to go from relevant to irrelevant would be, say, maybe the whole component, right, has one node active. Now if you deactivate, then everybody in the component, right, would become irrelevant. Or if you remove an edge, so this is the possible way, you have said this is connected, one of them is relevant, and you have an edge going from here to here. So these guys are connected. Now, even though there is no active node, but this one is, then everybody, right, is relevant. But now if you cut through this edge, remove this edge, now these guys that were relevant now becomes irrelevant. So we're going to answer for each node upon until which query 2,000 of them, where is the last query that will make it irrelevant. Okay, as I said, right, this question actually, if you go forward, it will be hard. Why? Because if you remove an edge, whether it is this edge, right, this node could be active, this node could be active, or they could be both inactive, or one of them is active. And also depends if this part there is an active node and then there is no active node here, right? If you cut this one here, it will change the status. So normally we try to avoid doing the removal. Actually, we do have right after this, the second unit we're going to do in the spring semester, that will be the destroying sets. The destroying sets would be a perfect tool to handle. You can add edges to a graph, and you're going to study after adding edges one by one. You're going to see whether the nodes stay connected or not, and you can find out how many connected components there are. So a perfect tool to do this one. But it only works the best when you add edges to the graph. If you remove edges, it's actually expensive. there is one tool you can still do that one. Actually, it employs a technique called rollback. So suppose you have added edges, now you remove them. So you're going to roll over to a previous status. So when you try to roll back, it is expensive to keep track of the information. So for this question, as I said, right, we're going to reverse the order. Why? Notice, so suppose we're going to perform all the operations, but we're going to remember all these queries in order, or remember all the updates in order, but we're going to say, just perform all the operations, deactivate or add an edge or remove an edge. Now we're going to remember the final status, the final format of the graph. Some nodes may be active, some nodes may be inactive. Some edges are added, some edges may be removed. So we're going to start with a graph that has some nodes. I'm going to remove this one here. So I'm going to start, maybe this one is here, there's one here, there's one here, there's one here, some like this one here. Some of the nodes, so each one, right, I'm going to say they are connected. These edges have been added and they have not been removed. Okay, these also have been connected. There's one maybe just by itself, and some of them like this one, like this. Anyway, so the nodes in each component, they should be connected. And some of them may be active. Okay, initially all of them have been active, but some of them after the operations, right, queue of them, some of them may be inactive. So for example, here, all of them have been deactivated. So here, right, all of them, they are irrelevant. Okay, when I say the disjoint components, inside each component, all the nodes are connected. But in between different components, they are disjoint. There is no edge connecting the nodes between them. So that's the idea for the disjoint components. Okay, now actually we're going to reverse. So the queue updates, right? We're going to follow all of them here. That's the final status of all the nodes, the edges. Now we're going to go back. We're going to go back. So suppose you had removed an edge, right? This say suppose was the last edge we removed. Now I'm going to roll back here. So this one, if you go forward, that's to remove an edge. But if you go back, so I'm going to add an edge. Okay, if you add an edge, if both components do not have any active nodes, then they still would be irrelevant. But if one is active, then you're going to change the status of the other one, right? This one was active, that's okay. Everybody here inside was relevant. But here, since there was no active node, so before everyone was irrelevant. But if you add this edge, now everybody becomes relevant. So this is actually the moment. If you go forward, this is the moment. Cutting this edge away would make these guys from relevant to irrelevant. Now, if you go back after adding this edge, right, the status change, I mean, the order changes, right? So it will go from irrelevant to relevant. Okay, remember, right, we have added an edge. Adding an edge is always easier to do. Okay, that's one way to do, right? Remove an edge, and then I'm going to say go backward, that's to add. You can, of course, sometimes, so add an edge would be the same as, I mean, it would be this within the component, then does not make any difference. Okay, anyway, we don't worry about that one, but we do pay attention to such in addition of the edges. Okay, another one is this was the say removal, now becomes add an edge. That's good, we are happy, right? Change from irrelevant to relevant. Now if you say deactivate, so deactivate, let me just draw another component. So here it was, okay. Okay, so this was active. If you deactivate, right, this becomes irrelevant. Now we're going to go back the order. Deactivate and now becomes activate. So now this becomes active. So if any one in this component, right, becomes active, then the whole component becomes relevant. So here this would be say activate a node. Okay, that's also good. It will go from irrelevant to relevant. This is actually the step, right, for those guys to go in the forward way, going from relevant to irrelevant. That's the answer we're going to report for these guys. So when you go backwards, you go from irrelevant to relevant. That's the moment. Okay, notice. Okay, there is a question. Good. Oh, for relevant, if a node is connected to a node that is active, then we say it is relevant. If a node itself is active or it is connected to a node that is active, then we say this node is relevant. Good. Okay. And observe, right? Once a node, if you go backwards here, once a node becomes relevant, can it go irrelevant again? If you add an edge, does not change that way, right? The worst would be say both components are irrelevant, after adding this edge still irrelevant. That's okay. But do you think it's possible a node will go from relevant to irrelevant? These two operations you can't, right? Remove an edge now becomes adding an edge. Deactivate now becomes activate, not active, activate. Activate a node, of course, will only make it from irrelevant to relevant. Okay, but there is another one, right? We say add an edge before, now becomes remove an edge. Okay, now this is important. Remove an edge, we don't want to deal with it normally. But remember, right, we say add in an edge in the description. You only add an edge that were between two nodes that are active. So suppose you do have two, me use maybe something here. Come on. Okay, so these two were there before. So we're talking about this was the big component. So before they were connected. Now, if you cut through this one here, okay, keep in mind, right? This node and this node both are active, and then you can remove the edge. To add this one here, there is no restriction. To activate, no restriction. But to remove an edge, since here, right, to add a node, but add an edge between two active. So that means you can only remove an edge between two active nodes. If you remove an edge between two active nodes, does it change the status of these guys being relative? Of these guys being relative? It does not. If this one is active, this one is active, right? If you cut off this edge here, does not change the status. Even though this becomes two components, still, each one still remains, each component still remains relevant. So from the perspective, from the viewpoint of checking whether a node is relevant or checking a component is relevant, this one does nothing change. There's no change at all. So basically now this operation, you can ignore it. Okay, hope this makes sense. Okay, for a lot of students, this disjoint sets would be a perfect tool to solve questions like this one. Also very similar to the question I just mentioned, right? Closing form. So some students did solve the question using the disjoint sets. That's good. Okay, but since most of you, right, have not done this, so we're going to take another one. Actually, this is from Danny Mental's version. Actually, it is smart. Okay, so we're going to talk about, right, the three operations, RDA or ADR here, right? A, we're going to just analyze, right? We're not going to do anything because it does not change the status of whether a component is relevant or not. This D, actually, we're going to do something. Once a node becomes active, then you're going to change the status of all the nodes in that component to make it relevant. And actually, for all the nodes in that component, that would be the answer, because that is the time that the moment they become irrelevant to relevant. That's the same thing. If you go forward, that they go from relevant to irrelevant. And as I just said, right, there is only one time you can go from irrelevant to relevant. There is never, if you go backwards, you will never go from relevant to irrelevant. So the status change can only occur once, going from irrelevant to relevant. And whenever that happens, that's the moment to report for all those nodes in the component. Okay, so when you have this here, activate a node, just propagate the information. So, hey, everybody in the current component, your answer would be this moment. The same, if you add an edge, if both nodes are irrelevant, you don't change it. But if any one is relevant, then you're going to propagate the information, right? If this one is relevant, then you're going to change in case, right, the other one does not have, was not relevant, propagate the information, or vice versa. So as long as one of them is relevant, then propagate the information. You say, well, how many times I need to propagate the information? Turns out for each component, you're going to just do it once. The reason is once a component becomes relevant, you don't have to update it again. Okay, hope this makes sense. So even though it's right, I'm going to add an edge and propagate the information. Maybe add another edge here. Change the color to make it okay, green. So suppose there is another one. Okay, the component maybe like this one here. Like this one. So you say, I'm going to add this edge. Do I have to propagate the information again? You don't. If this one is already active, right? You don't have to do this anymore. You can just do the other one. If you say this one is active, but this one is also active, then you don't anything. You don't have to go through. You can say, check this one here. If it's already active, don't propagate the information in the current component. And also here, how do you decide the component? Well, if you use the disjoint sets, actually you can. Each one you're going to find out the representative. So that's normally a way to decide whether you two belong to the same component. But here, since I said right here, you only propagate once. So you can just use the simple ADJ, the adjacency list. That should be enough. Okay, so now these two, we are also happy. If you add an edge, you're going to activate a node. The complexity is just, you're going to do the number of the queries. Actually, this would be the number of the edges, possible edges. Could it be less than this one, but the asymptotic should be the big O Q and also N here. Not Q, big O, this one here. So easily we can finish this in within the time limit. Okay, so this one I can go through. This one actually does not involve much the fancy concept. Actually, you can do the disjoint sets, as I mentioned, right? But you don't have to. Okay, I'm going to show here one way to implement this idea. This one I'm going to show you a Java mode, a Java version. So this is the form. This is ADJ. So typically we're going to have a list of lists to represent the neighbors of each node. And that's the answer we're going to report at the end. Why we want to make them global variables? Because in this recursive function, the DFS, because we're going to do the DFS, accessing the answers, and also do the ADJ. So we're going to make these two variables global variable so that you don't have to pass them through. So whenever you do the DFS, you can say X is current node, the time, this the moment, right? If this one has been set before, that means it has been changed from irrelevant to relevant, then you don't have to do it again. It's never going to change from relevant to irrelevant. So once it's activated, it's always active. Otherwise, you're going to say, hey, for this X here, right, the answer is T, the moment T here. And then for each neighbor B, okay, so each node should have a list of the neighbors. So B is a neighbor of X here. We're going to say visit node B, and also the time moment is the same for every node in the same component or connected to X here, right? All of the nodes connected to X, they should have the same time moment, unless this T was changed before. Okay, so now we're going to, that's the only helper function we have in this program. So this down here, right? There's an helper class for edge. So edge, because here we have the, you have to remember the edge you remove. So this one is basically remember which edge you have removed. Remember the going from where to where. Okay, so now N, that's number of the nodes. Q, that's number of the updates. You can say the queries. I think it was meant to say queries, but changed to updates. The ADJ to make sure you have associated a list for each node here. And we're going to do the, when you read this one here, you don't do zero based. When you make one based, make sure this one starts from 0 equals N here. Answer, that's also make it one based. The edges added here, that's the in order. Edges removed, you're going to remember which edge has been removed. Deactivated, that's for the nodes. Okay, hash set for this always active. So if a node started from active and toward the end has never been deactivated, then it will always stay active. So initially we're going to add all of them into this set, and then when we process the queue queries, we're going to update whether a node becomes inactive. So it goes from 0 less than Q here. When the first character, so this is the way to read the type. If you want to read one character, you have to read the string and then get the character at 0. If this is D, you're going to deactivate node X at a time T here. And now this X is no longer active. So we're going to remove this one from the hash set. If it's A, you're going to add an edge. So you can say added. This is the list of the edges, right? We're going to say add this one, the new edge X, Y. So both are one based. Remove an edge. So you can say remove the edge K here. K is one based, but we're going to put this one in the added. This is 0 based. So alpha by 1. Now this added, this edge right at position K minus 1 is no longer an edge, becomes empty. So here this is null. In Java, you can represent a null object. That means pointing to nowhere. So you cannot access it, but you can check whether an object is null. Okay, so after this part, we process from the beginning to the end. After we have done this one, we have recorded what nodes are active, what nodes are inactive, and what edges are there and what edges have been removed. Okay, now we're going to modify or update the ADJ here. So for each edge here, added would be the list of the edges, right? Even though some of them may be inactive, may be removed. So if this edge is not null, that means it is still an edge being used in the graph. So we're going to add the two. So this is the basically right A, B. So B is a neighbor of A and A is neighbor of B. And also we're going to find out the components where the all the node X, if it is active, then the answer should be Q for them. Why? Because up to the very last, they are still active, right? So the answer should be Q. Okay, find out all of them that are connected to those nodes X and mark them. The answer should be Q. Now we're going to process the rest. Okay, those that have been marked red, you're never going to change. Okay, once the answer array entry has been set, then you're not going to change anymore. Now we're going to go backwards. The queries, you go from Q minus 1 down to 0. If this, at this moment, right, we have deactivated a node, now we're going to activate the node. So now for this node here, deactivated T, when we did this one, deactivated T, right, is this node X. So for this node X here, we're going to process DFS, that's a graph traversal, say, hey, your moment is this T, because go backward, you go from irrelevant to active to relevant. So we're going to say for all the nodes in connected to this node X here, this is X, we're going to mark the timestamp is T. Now, if this one is remove an edge, now becomes adding an edge. So the two, if removed T is not null, so here, if you have added, no, second, oh yeah, here, remove this one, removed is not empty. All others, right, will be empty. So here you have removed this one, it's not null, that means we actually removed an edge. We're going to say remove this one, the from and to the two nodes X and Y here. Now add back, add the edges back. Okay, in terms of the adjacency information. So add Y to the neighbor list of X and add X to the neighbor list of Y. So that will show X and Y become connected. Okay, so if the time moment for X is not 0 or Y is not 0, then we're going to try here, try to spread out the information, say dfx and t, and dfx y and t here, right? So if they were irrelevant, now they should be set to t. But okay, don't worry about this one. What if X is already active, right? Then you don't do it. So you would never do it twice. Okay, so now that's to activate add an edge. And then if you remove an edge, as we just said, right? If you remove an edge between two nodes that are active, then it does not affect it. So do nothing. So life becomes actually much easier. And then at the end, we're going to say print out each one. If you do the Java, this may be a tiny detail here. If you print, use system.out_print for n times, actually it may be time consuming. Well, here n is up to 10.5, so could take maybe 0.2 by 0.3 seconds to print out. One way to make this one faster is you're going to use a string builder. So you're going to say the whole content would be saved in this st here, sb, and at the end just call the command print once. So this will make it faster. Again, for this question probably does not matter, because if you do so, the complexity is big O n plus q, where O and n are both in the range 10.5, so it does not matter. You're going to finish maybe within a second or at most 2 seconds, even in Java. So with or without the string builder does not make any difference. But sometimes you may, especially when you have to write, for example, close to 250,000 of the integers, then probably the string builder will save you some time. Okay, so this is the second one. Again, right, this one, this solution actually, it's very smart. You can say this can also appear in a silver level contest. But I know, right? It says this is already hard. It's quite a challenge. And you say you want to put this one into the silver level. That's unfair. Okay. At this rate, this one typically people would try to do with a the disjoint sets. But turns out you don't have to. The reason is because you only need to figure out in a disjoint set whether there is any node that is active. So that's the only property you need to remember. And then propagate is easy, just propagate once. That's guaranteed to be efficient. So here the graph traversal, the DFS or BFS would make life easier. So I'm pretty sure when the question was created, this was not at the beginning. And then turned out if you don't have the restriction, it will be much harder. But now with this condition, it becomes much easier. So kind of a dilemma. Okay, so far we still have not seen any question. You have to deal with the removal of the edges. Closing the form and also the YouTube, the videos, and also like this one, you can always change the order and then handle the addition rather than the removal, and life becomes much easier if you work with the addition of the edges. But it's always a good idea, right? You know, there is a tool you can, even though it's not as simple as the disjoint sets, you can, I mean, the typical disjoint sets, there's still ways you can do it. As I said, right, you can do the rollback, even though it is tedious, but you can still do it. So when n and m, the number of nodes and the number of the edges, right, are not that big, then you can still finish within the time limit. Okay, do a little research and you can find out that one to handle the edge removal. Okay, I think we have time to maybe talk about this third question a little. This one, actually, the only question we have covered. The graph traversal, and here, okay, if you have taken this one here, the spring, the fourth semester, we did cover this topological sort. So this question actually can be solved using topological sort. You say, hey, how come? This question actually is kind of weird in the sense, looks like I have no idea where to start. That's why here the answer is also kind of weird. The answer clearly is not unique. So you can print any K and any sequence. As long as it's satisfying the restriction, then should be fine. This is not typically the style for USACO. USACO, to make it easier to judge, the answer more or less should be unique. So clearly this one is could be refined. I'm pretty sure if you, keep working on this one, you're going to come up, maybe make modifications and make this question more unique, the solution, to make the grading much easier. Otherwise, grading would be kind of tedious. You have to examine the conditions one by one. Okay, let's look at the question here. Suppose we have an array x1 through xn non-decreasing, and find out for each I here, find out the index ji, so that ji would be the last index, so that this condition is still true. If you go one more, so xji is less than or equal to xi plus k, but xji plus 1 is bigger. Okay, so would it be like this? Less than xji plus 1. Not this plus, so should be this one plus 1. So the I should be the subscript plus 1 here. Okay, so from the Java jargon, this one is the last index. So from the C++, that's the upper bound -1. Upper bound would be the one that is bigger than this one here. The one strict bigger than this one, the lowest, right? -1 would be the last one that is less than or equal to. So we have the array ji. We don't have x, rather we have the ji array. So j1, j2, all the way through jn. Now we're going to find out a sequence x1 through xn that will satisfy the restriction. So we see the I array, that's 1, 2, 3, all the way to n. We see the ji array, that is j1, j2, j3. So in this case, right, we're going to say 2, 2, 4, 5, 6, and 6. So 1, 2, 3, 4, and this one is 5. And this is 6 here. So the solution clearly is not unique. Okay, easy to see, right? If an array, a sequence x1 through xn works, then plus any constant should also work. Right? Because if you add a constant, this will still be true, right? Plus 2 for each one here, that's still the same. So the answer clearly is not unique. So we can easily, right? We're going to assume, say maybe x1 is 0. That will make it unique for one thing. But still, that's not unique. Okay, so try this one here. So we're going to do this one. So that's the X array. That's 1 and 6 and 17. Actually, it's also not unique here. 16 and 22 and 27 and 32. So for this, the first one, so that's X1, K is 6 here. So let's make K 6. So 1 plus 6, that's 7. The value that is closest to 7 is this 6 here. So X2 is the one that is less than 1 plus X here. No, 1 plus K here. Now for 6 plus 6, X2, right? 6 plus 6 is 12. Still itself is the closest one. So by itself, it's 2 here. Because the next one is 17. 17 is bigger than 6 plus 6. Now 17 plus 6, 23. Then this one is the closest from the lower side, from the left-hand side, right? So here it should be 4. And for 22 here plus 6, that's 28. So should be this one closest. 27 plus 6, that's 33. Then should be this one closest. And this one itself should be itself. Xn is always, so here if you have n, this number is always n for sure. Okay, so it is kind of, to solve the question is like standing middle of nowhere. Where do I get started? Okay, so for this one, we're going to have the restriction. If you have the ji for each one, right? So xji should be less than or equal to this here. If xji is bigger than xi plus k, then this one is not allowed, right? Xj has to be less than or equal to this one here. Then you're going to reduce this one when you do the assignment. Okay, the same thing here. If xji plus 1, if it's bigger than this one, that's fine. If this one is less than, so if xj and I plus 1, if it's bigger than xi plus k, it's fine. But if this one is less than or xi plus 1, yeah, then we're in trouble, right? This one should be bigger than this one because xj would be the last one to satisfy this inequality. This ji plus 1 should not be here. Then in this case, xi, you should make it bigger. Or you say, right, this one, you should make it smaller. You should make this xji plus 1, right? Make this number bigger or make this number bigger. No, I'm sorry. Make this one smaller, right? Make this one smaller, then this one will stay, but this one will make smaller, then this is no longer true. So we're going to build the relationship. If this one is the case, you say, hey, there is dependency from x to xji here. If this one is true, we have a dependency from here to here. All right, okay, so this is the idea for the topological sort. Topological sort, we're going to find out one way to so you have all the directed edges and maybe okay, these two may point to the same thing here, like this one here, and maybe like this. So you want to go through these guys. There is no restriction. They don't depend on any other, right? You can process them first. Once you have processed these guys, then you can process these guys. But you cannot process this one first before doing this. right? Like the assembly line. If you want to work on this one, you have to make sure this part is already ready. So you have to do this one first. So a topological sort, right? You're going to say sort the nodes so that if there is an edge between X and Y, X would always appear before Y. That's how you do the topological sort. And the way we just did, right? If this is the case, you have a dependency relationship X to Y. So you're going to process those that are free of the restrictions. Those should be assigned first. And then for the others, make sure it satisfies the restriction and you can assign them. So we're going to have a queue to process the nodes in order when the in degree becomes 0. And as we said before, right, the number of the ways to do the topological sort is actually complicated. That's why normally you're going to just get one sorting. So here I'm going to show you another way here. Not much time, but I'm going to just go through here. N is number of the integers. Resize, these are just for the arrays. The J array here, adjacency information to record the dependency. This one is actually, I think, no, wait a second. This one should be changed to change. My mistake. Yeah, okay, everything else should be fine. And this is the array that we're going to do. That's actually the array X. And then the in degree, right? When you see this one, the in degree, then kind of, you know, this is the topological sort. Okay, so here, read the J array here. Now this part, hopefully this makes sense, right? Z at I, that's Xi here. You can assign this one to be Z at Ji plus 1 minus K plus 1, right? Z at this one should be bigger than Zi plus K. So we're going to make it one more than this one here. Hope this makes sense. So Z at Ji plus 1 should be bigger than Zi plus K. So you can make this one Zi plus K plus 1. Oh, by the way, let me close everything here. Here we use set this K to be this one. Actually, for any K bigger than equal to N should work. Now, this is a function that would be interesting. So we're going to say connect. So we're going to add an edge between the two. So just to go through this quickly here. So you want to do the A to B here. Suppose ZB is less than ZA plus W. W is whatever the K, right? If it's less than, that's fine. It is in here, there's no restriction. But if ZB is big, then we're going to do this one here. We can add, so A has a, B depends on this A here. And we're going to increase the in degree of B by 1. Okay, so this one will try to add the dependency. If this condition is not satisfied, then, you know, they are dependent. So we're going to just, I don't have time to go through the details, but anyway, so we're going to add the dependency here, I and Ji here. They should be restricted by, separated by this K here. And going back here, Ji plus 1 and I, they should be connected by this negative K minus 1, depending on which direction. So going from low to high, that's positive here. Going from high to low, that's negative here. Anyway, so if they do satisfy the restriction, then we're going to add the edges. Now we're going to do the typical, the topological sort. For all the nodes, if the in degree is 0, added to the queue, and then we're going to process this queue. As long as the queue is not empty, always take the first one and check all the nodes that depend on this current. So there is an edge going from current to P. Find out for this neighbor here, how much change you need to adapt. Going from below, how many restrictions you're going to have, and modify the change. And if this one is for this neighbor, right? If the integree is 0 after you -1 here, because edge going from current to P, if this current has been processed, then this edge no longer exists. So we're going to reduce the integree by 1. When the integree is 0, we're going to add this neighbor to the queue here. So hopefully we're going to be able to find a topological sort of all the nodes. It's proven. It says, right, it can be proven. This is always possible. So that means this loop will finish and then the queue would be empty and there is no cycle. And at the end, we're going to say add to each number here to the change. The change is necessary to satisfy all the restrictions. At the end, just print this one here. And etc. Right? You can remove, I mean, you can subtract a constant to each one here. So does not matter. You can just print K and any number, as long as the numbers are in the range, but the range is so wide, so it does not hurt. So even though you start this K to be 10 to the power of 18 still works. Why? Because you only have 10 5 numbers. So to make it one odd bigger, you have to actually no, 13 is the safe bet because we have 10 5 numbers. So still 10 13 would be enough. The safe bet, but actually you can just make it n+1 or n+2, or actually n is enough also. So anyway, so for this one, if you want to check your answer, you have to write another small utility to basically check for each one whether the JI is the last index satisfying the restriction. So it'll be fun, okay, for each one of the test cases, right? So work on them and then see whether you can get your answer checked. Actually, if you want to just compare your answer and with the answer provided by the USACO web server website, actually does not work because the answer is clearly not unique. So write your own utility. All right. Okay. As I said, 2 hours for the 3 questions actually would not be enough. Actually, I just walked through the code in a brief way, and you may still have a lot of confusion or questions, but stay in the class and we're going to go through all the confusion, all the techniques in great detail. So I'm looking forward to seeing you guys next week. All right, I'm going to stop here. So see you later.